Good afternoon, colleagues, students, ladies and gentlemen, friends. I'm Anderson Shum, the Vice President of Research of City University of Hong Kong. First of all, Happy New Year to all of you. If this is your first research seminar here, I hope that you have a successful and fruitful year in 2026. It is my great pleasure to welcome all of you to today's research seminar, and in particular to welcome Professor David Juncker to here. So this research seminar is our platform for advancing scientific discovery and collaboration, and more importantly, scientific exchange and discussions. We are very pleased that we have Professor David Juncker, Canada Research Chair in Bioengineering, Professor and Chair of the Department of Biomedical Engineering, and Principal Investigator at the McGill Genome Center at McGill University in Canada. Professor Juncker and his team have introduced innovative ideas in microfluidics, including capillary circuits and multiplexed cross-reactivity-free immunoassays. His work has led to 2 spin-off companies and applications in point-of-care diagnostics. Many of these areas are related to some of our key focuses of our Biomedical Engineering Department, as well as the Institute of Digital Medicine, also align with our efforts and vision in both internationalization and innovations. So I hope you enjoy some of the sharing of the insights by Professor Juncker later on. Today's seminar is titled Microfluidic Mixer, Capillarics, LCD 3D printing, and Brownian motion-powered Sieve-Detector. Professor Juncker will share his journey with us, and please join me to welcome Professor Juncker to the stage, we'll, on behalf of the City University of Hong Kong, present Professor Juncker with a limited edition of our City U Hong Kong crossover camo thermals. We understand that Montreal may be a bit cold, so maybe with the thermals you can carry with you, and always remember that you have some connectors and friends in Hong Kong, in Kowloon Tong. For those of you who know, the Camel brand has crafted glass vacuum flask since 1940s in Hong Kong. So this is a very Hong Kong, very much Hong Kong product, and also still trying to innovate and crossover with City U Hong Kong and resonate with our pursuit of the research, innovations, and entrepreneurship. So with that, I hope you join me, and we'll present this gift to you. With that, may I invite Professor Juncker to deliver his anticipated seminar. Professor Juncker, please.
Okay, well, thank you so much. I'm trying to get the different things here. Just put this down so that I get some space. Thank you. Thank you so much for the generous invitation and for hosting me in this wonderful venue here. It's a great pleasure to be here with colleagues and friends and family. And it's also a great excitement to present you our work here and I call it microfluidic mixer in the sense of a cocktail mixer. Also, there's no cocktail drinks here, just some microfluidics. I'm sorry about that. But I hope we'll have a good fun and learn something out of this. And so, as I mentioned, I hope to make this a bit of an interactive presentation. So we have a good-sized audience that you're welcome to ask questions. And I try to ask you a few questions during the presentation as well, so that you'll have some memories out of these events as well. So I have a camel bottle already, but maybe you'll get something too. Okay, so let's jump right in. So I'm the one talking here, but this is really the work of a wonderful team. We have really amazing people participating here from all over the world. So Montreal in summer, it's a very nice place. In winter now it's minus, not today, but it's I think minus 17. I'll go back. So I'm happy to be here at this moment. The work is also the result of many collaborations. Well, actually, lately, a lot are in Montreal, and as well, of course, through the funding agencies that have been there to support the work over the years. So big thanks to all of them for making this work possible. And okay, I'm into microfluidics, and I'll take in the next slide, microfluidics is life. So we follow the stream of life, and so we got into different things. It's quite diverse. You want to learn more about the lab, you can go on the web page down there, and you can see our recent publications as well on different topics, and some of which I won't be able to talk about. Today I'll focus on three main topics here, which will be capillarics, so our version of capillary microfluidics, 3D printing and how they synergize with capillary microfluidics, and then also talk about something new and really exciting to us. It's the microfluidic sieve and digital analyte detector that really, I think, can have a big impact on assays and diagnostics. And that's then basically the outline. I'll have some kind of introduction. I'm not sure who is in the audience, so try to bring everyone on board. And then I'll go into 3D printed capillarics and explain, well, what we want to do, lab on a chip, and local, and also manufacturing, this idea of manufacturability, which I think is a big challenge too, if you want to go into applications. And then have kind of a different talk a little bit on the end. So I have quite a number of slides, but I try to make them quite flow into one another. So I hope I'll be able to carry you along the flow and the stream here. Okay, as I said, microfluidics is life. I think life, it's all a single cell. It's the founding block of life. And we all started as this little single cell, and now we're billions of cells. And cell is 70% of liquid, it's micro, it's small, and that's microfluidics to me. And so we have really opportunity to address many different questions in life. But when we speak microfluidics, actually, I just want to bring back people and also where the opportunity lies with 3D printing microfabrication. And you have a cursor here if I press long enough. Oh yeah, oh, how does that work? Where is it? Oh, okay, I think I'll just walk. Okay, 1 millimeter size, 1 microliter. And this we can easily 3D print, 1 nanoliter, 0.1 millimeter size, and that's actually the regime where we work at. And 10 micrometer size, that's microfabrication, but that's actually almost too small when we want to do analysis because we might not even have what we're looking for. So we'll be working more in the micro regime. And so when we speak about microfluidics, one of the big applications is lab on a chip. And when we think about lab on a chip, maybe you have been here, or maybe that's more my generation, looking at Star Trek. It's this idea of this instrument that can analyze all different types of markers. Now, more in our actual world, the way this has been progressing is trying to integrate many of these different processes into a chip that traditionally were done in a lab, into a small chip so that they can be automated and be made faster and less expensive as well, because now you might need less sample and less reagents. And that kind of has been a big goal for the field, which started about 30 years ago. And maybe one of the illustrations of this, the science cover, which is already 20 years ago here, with this multi-layer soft lithography chip, which was published by Quake. And there's an analogy here with electronics, where we have this multiplex control that can operate a lab on a chip type of structure. Now, when we speak of lab on a chip, that's one of the technologies, but you have also technologies like centrifugal microfluidics or digital microfluidics, where we move droplets around. But maybe what characterizes them is that typically we have a small chip, and then we have a peripheral box, and then we have a computer that is being used to program these systems. And so we call them lab on a chip, but I think it's a bit of a misnomer to this point, and that's maybe a bit a bad look for the field, because it's still a bit lab around the chip. And so there has been a lot of progress to making the box smaller, but unlike your cell phone, which is really self-contained, these are still not really self-contained chip. And so maybe again, to shed a bit of a critical light on the field here, maybe the one type of integrated microfluidic lab on a chip we're having are kind of these lateral flow tests, which I think we all know from the COVID period nowadays. And they meet this kind of affordable or assured kind of criteria from the WHO, which are affordable, portable, user-friendly, equipment-free, and cost-effective. But are they really a lab on a chip? When we think lab on a chip, maybe we think about something that's versatile and programmable, and also something that's scalable and that can handle many different things. And so, I'd argue maybe not so much. And so what I'm proposing today and what we kind of have been trying to work towards is to make a programmable lab on a chip that has no peripherals, no moving parts, that's electricity free. So that kind of reunites some of these capillary microfluidics, but that's also digitally manufactured and that's also programmable in a much more advanced way. So that's what we basically in our language call capillaric circuits. It's kind of a word we coined because it's capillary-based flow, but capillary has a lot of different meanings, both for capillary electrophoresis as well as for capillary pressure. And here what we wanted to convey also is the distinction between capillary phenomena, like in electronics, where you have electrical phenomena, and then capillaric circuits. So like in electronics, you have electronic circuits. So electrical, electronic, capillary. And now what the great power of capillary microfluidics and capillarics, it's that they're self-powered. And maybe the one relationship I would like you to think about is simply that the capillary pressure here scales as 1 over R, and so the smaller the channel, the higher the pressure, and the higher we can drive the flow. And so they're kind of self-filling, so people sometimes call them passive. I would challenge that they're actually, that language and saying that they're actually active because they're actually the one that self-fill. And what we need to do then is to control the surface chemistry of these systems, and this so that we have this spontaneous filling to make them hydrophilic, and this can be easily done with a plasma chamber or some chemical modification so that we can have a contact angle that's low enough for self-filling but not too low so that we can still control the flow inside of these systems. And here we can also then the surface tension. This is 1 over R relationship multiplied by the surface tension of the liquid and the wettability of the contact wall. And when we think now about a microfluidic circuit, we can then establish a simple relationship like in an electronic circuit where you have Q, the flow rate is the pressure, U divided by the flow resistance. So it's really like an electrical analog where you have E equals U divided by R, and R is then given by a relationship that depends on the dimension of the channel. Now, one little trick here, when we think about capillary microfluidic, people often think about the liquid at the filling front, which drives the liquid, but we also have a liquid at the back because everything has a beginning, everything has an end. So we have pressure that applies at both parts of this system. And what we have been working on is actually trying to control the flow through these both aspects. And by doing so, we can then start to integrate different functions into these structures that replicate the functions that we have on the left there. So you have this, this symbolic representation of the functionality that's programmed into the structure of the microfluidic chip. And as we speak about microfluidics, manufacturing has really been a very important part of that, where we started microfluidics before the microfabrication revolution, which then really introduced the concept of microfluidics. And now we're moving towards these 3D printed microfluidic structures that now enable us to do much more advanced systems. And this is, and so we have now this synergy between microfluidics and rapid prototyping, where we quickly can iterate capillary microfluidics and make them work. And so here I'll just have a brief vignette on 3D printing, which is the other aspect that I'll talk about. And here we speak about photopolymerization 3D printing, which is a technique from already 1986 that has been used to print structures here. And here it's a very simple concept. You have a photopolarizable bath. You use a laser to polymerize a small structure. Just where you want to polymerize it, you lower it into the bath, and then you repeat it layer by layer. Now, modern 3D printers, they still can use the same concept for laser scanning, but now what we're doing, we invert it, and we typically polymerize at the bottom of a vat. And we can also do that with digital light projectors, where we use the same, but we have a light projector, and it's not a projector, it's a screen, I think. But we can then direct the light and photopolymerize at the bottom. And so this has now advanced to the point where we can buy these printers, and you can see pixel sizes 50 to about 27 micrometer square here, and 2 million to about 4 million pixels with this DLP type of printers. And here, this technology has had a big impact, but it's still only something that's reserved to a lab. And so here's a brief summary of how this works. You go into the vat, you expose the system, you raise it above, new ink flows in, you re-expose. And for microfluidics, the big trick is actually to make these empty parts, because when you re-expose a new part, you have to be careful that you don't clog that one. And that's where the big limitation lies. And that's where we cannot yet achieve the same resolution than the pixel size, but still small enough for making microfluidic systems. And so once we're there, then we can buy inks, which include a monomer, a photoinitiator, and a photoabsorber, or we can make them ourselves, which we're doing out polyethylene glycol deacrylate, and build, in this case, biocompatible microfluidic systems. Okay, and so, well, what can we then do with this microscale photopolymerization? Obviously, it's this microfabricated microfluidic capillary circuits using a protocol that's outlined here, and that we kind of developed. And using a 3D printer, we print them, we use IPA, here's PEGDA inks we often use now, we rinse them with IPA, we blow them dry, we post-cure them in an UV chamber, we activate the surface in an air plasma to make it hydrophilic, so we have the self-filling capability, and finally we cover it with a hydrophobic cover to ensure the flow controlled. So I'll illustrate now a simple delivery system of 4 solutions that encodes the simple programmability using a capillary microfluidic circuit. And so this system will embed stop valves as well as capillary retention burst valves, which are holding the liquid back at the back end of the liquid. So first we have the inlet, the reservoir, and the stop valve, and the retention burst valve that will become active at a later stage. So when we fill this, we have the liquid that fills to the stop valve, and that's a geometrical enlargement which prevents the liquid or makes it energetically unfavorable for the liquid to progress. And at this point now we can add the triggering solution, which could be our sample or something else, in this release channel and connect it to a paper pump in this case. And now simply by adding a liquid, we will trigger the liquid there. And now what we're having here is that we have at the back a capillary retention burst valve, and so there are 4 of them, as you can see here. There's a large one, a bit a smaller one, an even smaller one, and the smallest one. So which one? And so now we will start to connect the liquid. It starts to pull on these valves, and one of them will burst first. Okay, which one will burst first? You have, I think you want to add the blue one. Yes, why? The lowest pressure. Right, exactly. So that has a low capillary. So when we pull, it's like a tug of war. Everyone is pulling, and the one who can pull the weakest is the one with the lowest pressure. So so that's the weakest burst valve. And so when we pull, that's the one. And so now, without any computer, just through the structure, I could program the sequential delivery of these 4 liquids. And so what can we do now with these applications? Well, one of the obvious applications is to do a sandwich assay. I'll just repeat that because it's important here, but it'll also be important in the second part of the talk. And sandwich assay, very simple. We have a capture antibody. We incubate with a sample. We have a specific recognition. We have washing steps. We have a detection antibody with an enzyme, and then we add the substrate solution. We have a catalyzed chemical reaction, which converts an invisible substrate to a visible one. And that's then our readout if the sandwich was completed. And you go to a hospital, that's what they use, or in the lab, they take 2 to 3 hours. In the hospital, 15 minutes. The limit of detection is 1 picomole. That's detecting one protein in a concentration of micromolars of other proteins. So it's about 10 billion times lower. So it gives you a sensitivity of 10 billion times above the ambient. And that's like recognizing a single person among the entire world population. So they can do that in about 2 or 3 hours in the lab, or 15 minutes in a state-of-the-art instrument. So when we have this ELISA protocol algorithm, the one you would use in the lab, that's basically what it does. And so if you want to do that now with our capillary microfluidic, it takes actually many more steps. And unfortunately, this pressure-based control cannot accommodate as many steps because you have a failure of the flow. And here is where we then thought about how we could execute a larger number of operations. And this was what we called and introduced this new approach that we call microfluidic chain reaction. And as you will see here, that is inspired from basically chain reaction. And so chain reaction, we know it from a nuclear reaction, where one event, in this case the fission of an atom, triggers another event, which then upon fission triggers another event. And so you have this sequential or event-driven type of reaction. And this will continue until everything is used up, and then the reaction will terminate. And so how can we implement this in a microfluidic system is then basically the question. But before I get there, And here's another question for you. Do you have any idea of a macroscopic chain reaction? I showed you a microscopic one. Any of you familiar with this type of reactions? Anyone likes to play at home? I know Hong Kong is, I showed it before. They told me in Hong Kong, you guys don't do that because the space is too small. But I probably you have seen it online as well. Okay, so that's also an event-driven reaction where one domino falls, triggers the next one, and you can branch it out, and you can do little things. And so that's basically the fundamental idea that we also apply here, where we have now reservoirs. When one reservoir is empty, it triggers the emptying of the next reservoir, which then triggers the empty of the next reservoirs, and then propagates along. And we can also branch it out, where one reservoir triggers two reservoirs, or we can repeat it. So here one reservoir triggers two, they have some mixing, and then you conceptually, it's like an algorithm where you have a loop where it will repeat the same action, except like that, like an algorithm, of course, we need physical space to repeat these events. And so this was then implemented, so we call the microfluidic chain reaction using what we call a domino valve. And that's shown here, where you have an air plug. And so we have a stop valve here and a retention valve. And so we fill the liquid, and this valve, this pneumatic system is in between. And so when we empty, the air will come in here, but only once this reservoir is empty will the air be able to go to the next reservoir and then propagate along. And I'll show that in the next video here that illustrates that, where we have the reservoirs that are there, the air links, and the vent. So the vent is not really visible here, but it's just here. So you'll see it when it triggers now. So as before, we have this. Now we come, we trigger. And now we have the air that comes in here, that empties this one. So fairly straightforward. And once that is empty, then it triggers the next one, and that is empty triggers the next one. So there's two channels here that are progressing, right? There's the liquid flow at the bottom, and then there's the air channel at the top that are progressing here in opposite directions, actually. And so here I show it with 6, and we have shown, if you go to our paper, that you can do that up to, that paper at least 300 events like this, and that you can then use that to execute fluidic delivery functions. Now coming back to an application here, so the ELISA, this is the macroscopic ELISA with the pipettes. So now can we adapt this ELISA protocol to a microfluidic chip? And in this case, we reduce now the time for all the different steps, but we maintain the ELISA system where we can use the good washing to improve basically on lateral flow assay, the rapid test type of performance. So that's what we call here the ELISA chip. For now, we have a chip that has no peripheral, no computer, no electricity, and that's pre-programmed and actually made by DLP 3D printing, so it's also kind of digitally manufactured, or almost, to execute an assay like that. And so this is then the video illustrating this system here, where now we have pre-filled all the assay reagents. This is a COVID-19 antibody test, so you have COVID RBD, COVID protein on the surface, you flow the sample. If you have antibody against COVID, your antibody will bind. Then you have a rinsing step. Like in a classical ELISA, you have these wash steps, which help us reduce non-specific binding, followed by an anti-human IgG antibody. So if you have an IgG binding there, you'll have the binding, then streptavidin with the enzyme. And then if you look here carefully here, at the bottom, you have the substrate and the conversion and the precipitation of a solid enzyme that reveals both the control line and the positive test on this system. And so that works great, and I'll show you some more detailed results about this type of technology. But I showed you digital manufacturing, and maybe you will kind of have some concerns because manufacturing is still a lot of steps here. So one of the questions we had, and actually that was also, I think, through my visit in 2018 with Cecil, who said, oh, can you make chips that are hydrophilic for a long time, that we can take them out into the field? Can we improve on this manufacturing here and also circumvent the use of the air plasma chamber, which is cumbersome, and also it's not stable long time. And so there the idea was now to modify our ink. So, we were a microfluidics lab, now it became a bit of a materials lab, where we try to work on the ink to make it hydrophilic on a longer term. And in our case, the approach that we took here was to use a cross-linker, acrylic acid as a cross-linker, to add it to the ink. And then when we do that, we could, upon cross-linking the resin, we could reduce the contact angle to about 30, 40 degrees. And that's low enough so that you have spontaneous filling, and high enough so that the liquid stops at the stop valves that we have in our system. And now we can simplify the manufacturing process, where we just have make or download a digital file, print, rinse with IPA, nitrogen, and then make your chip. And so I think you can maybe almost do that at home now, and so that then also opens the opportunity. And using this approach, here's a chip now with still with embedded channels here that was 3D printed using one of these hydrophilic inks. And so so this kind of works. We still have improvements that we're working on, and that we're making it more stable and long-term stable as well. Okay, now I showed you so far the work with laser scanning and DLPs. And so this work typically at 385 nanometer, but I think where we have kind of a microfabrication, maybe a revolution, not a revolution in terms of capacity, but in revolution in terms of accessibility. And this revolution is driven by these LCD printers now. Most of them are actually made in China. And we're not working at 385, we're working at 405 nanometer. But the big change here is that the cost of these printers is about $200 to $600, so really something that's really affordable for you to buy at home. It's basically cheaper than your cell phone at this point, or many of your cell phones probably. And what's not only great is that they're not only cheap, the number of pixels they can have, if you look at the last one here, 58 million pixels, way above what you can have with DLP printers, and the pixel size is actually competitive. And that's from a year ago. Now you have even printers with 76 million pixels, so that even more performant than this one. And so this really makes it very accessible, except we have a different wavelength, and we have a low light intensity, so the inks that we're using for DLP, they don't work directly for these LCDs. And so we worked then basically to improving the inks also for the LCD printers, and while maintaining low viscosity inks, which you need for the filling. And in this case, our first effort was to use a cross-linker here, PETA, to try to improve the ink. And now the same microfluidic chip that we did before, we can make it with the LCD printer here. And we can now, and we also reduced a bit the time of this chip, and we applied it in this case for interferon gamma, which is an inflammatory marker, a cytokine, to run that chip. And here's an example now of this LCD 3D printed chip, still with a paper pump here, where we have the same sample, but here it's an antibody that is on the stripe here, nitrocellulose stripe, and then we bind the interferon gamma, target the interferon gamma, but with the same sandwich structure. And so our limit of detection is 12 picogram per milliliter, so this is really competitive in our hands with the ELISA we had, except it's just you put the sample and you walk away, or all the reagents and you walk away, and this runs automatically. And we also have a very good CV after optimization here of 6.8%. Okay, now I showed you digital manufacturing, so can we really use that to manufacture devices? And I'll just show you one little illustration here using an organ-on-a-chip application to illustrate the potential of the digital manufacturing here. So this is just a structure in PEGDA where we have two spheroids that then can communicate. It's really small. This is a Canadian $2 piece, so that's one of the units. But now, thanks to the LCD 3D printer, we were able to print these structures, for example, in a 96-well format. And because the LCD printer bed is so large, we can even print 3 of those at once, and it takes about 1 hour to print 3 of these plates. Now, if you're a bit more ambitious, we can also print them as individual little pieces that you break apart. And in this case, we could print 3,000 devices in one 8-hour run with one $300 printer. So if you have 10 of these printers, you could print 10 times more of these structures, which illustrates the potential for digital manufacturing of these systems, because unlike classical manufacturing, no tooling involved. You send me the file, I can print it, as long as it matches the print capability. Now, if any of you is interested, all our files, or most of our files, or all our files should be there. If they're not there, please let me know. We can upload them. So you can download them and play around and try to print them in your lab. And so that's what I said out. I was saying I was going to do. I hope I've been able to convince you that this is kind of what we're able to do with this capillaric circuits type of technology. I think we have also some demonstration that it's versatile and programmable. We have other applications such as blood clotting that we explored. We can make maybe other processes. So if you have ideas, please let us know. And I think we can also have distributed digital manufacturing that can demonstrate that. So as a first mid midterm or mid-presentation conclusion here. Computer plus 3D printer can be my chip, can be lab on a chip type of application or organ on a chip type of application. And I mean, maybe speaking to some of the chemists here, the materials, there's really lots of opportunities improving the materials of these inks and resins. I'm not a chemist, so there's lots of people who might be much more qualified for that. But I think where we're excited is that really everyone could manufacture these, and we're also planning on a community printing, and I think some of you already expressed interest in participating, where we would help you to try to print and make these functional devices using an LCD printer that you might have in your lab. Since I'll change topic then to the other part, I don't know if there's any questions at this point. Yes. Right. Yes, that's great. Thanks for the question. So the 3,000 is a scaffold that you would break each device apart, right? So they would be connected with small links. So you would print everything and then you break them, and then you would have them as individual parts, right? So probably the well format is probably the one it's more practical one. But so if you want to print, well, like injection molding too, right? You have when you have sometimes multiple time, you have where the mold goes in, you have these parts, and then you have to break them off. So a bit same idea here, where you would have. Well, I think it would be here. It would be on this type of device, right? So here we have, 192 per plate, yeah. Right, and so the plate has then, well, the two has this structure here, right? Each has 1, 2, 3, 4 inlets in each of these little wells, and so we can have 192 on the 384 or the 96 well plate format. Yes.
That's the issue we used to have before with the microfluidic 3D printing.
So sorry, what issue is what with?
Polishing, like the accuracy of during the printing.
Yes, a lot of problems. So yeah, it's a trade. I mean, so see, the pixel size is 25 micrometer, but the features that we can print reliably is maybe 200 micrometer embedded structure, and mostly we like to print on the surface. So we're still working on really making it work well for embedded structures. And so it's a question of the smaller you go, the yield might go down, right? So you have to evaluate the performance of your printer. So also some printers over time, the illumination might be different in certain areas. I have more intense here, less intense there. There's a lot of fine tuning that goes until you can really print. I mean, the smaller the feature, the more tricky it becomes. And so that's why we work, 200 micrometer that's fairly okay. For embedded channel, you still have to be a bit tricky. You can't make very long embedded channels. They'll be clogged, for example. So you have to work around your parameters that work and work on them or adjust your design to make it printable as well. So it's still a trade-off, and it's not so there are some limitations there. And that's where there's also opportunity then to work on making this more reliable and more higher resolution. Any other questions on this part? Capillary microfluidic 3D printing? All good? Okay. Okay, so let me jump. Oh, yes. But so with the LCD printers, we could print the 3 plates of 192 wells on one print, right? And so it's about 10 millimeter per hour in thickness you can print with 20 micrometer layers. But so for some application, we have printed several hundreds of, like, we've had some, I didn't show it here, but some clinical trials with like point of care diagnostic. We print several hundred chips over time. So we can print enough, for example, to do a small clinical study, proof of concept study, right? Right, so that's kind of the design of this thing here, right? If you have a robotic pipetting system, you could easily go and then pipette into these wells. For this application, exactly right. So yes, I mean, well, okay, if it's organ on a chip, these are, typically it's days. So you pipette, maybe pipette your drugs in, different drug in each well, then leave them there for a while. So I don't think there the robotics would be an issue. I mean, if you think point of care, one of the things we're also thinking about right now, we still have to pipette in all the solutions before they run. Of course, you'd like to pre-dry your reagents, lyophilize, or maybe also have a pouch in there. So that's the kind of thing so that you could automate it further. And then you can print, I mean, chips like this diagnostic, you print tens of chips, maybe on the larger LCD printers or in one run. So it's not competitive with injection molding in terms of mass manufacturing at very low cost. But if you have a new design, I don't have to make a tool. I don't have to make an injection molding tool. I can print it right away, right? So that's where some opportunities there. Or if you're, let's say you're interested in developing new diagnostic technology and you want to commercialize it, well, maybe your first prototype could still be 3D printed, right? Because you could produce tens of thousands of these chips or millions of chips a year by 3D printing. Maybe not 100 million, but maybe a million. Yeah. Well, if it's biology, of course, the biological materials you want to put in, that's very expensive. And so here, I mean, if you want to go into biology, I mean, the biocompatibility is still a big bottleneck. So here we did 5 days, for other application 12 days culture, but if you want to do months culture, there's still toxic, the photoinitiator, photoadsorber, they can be cytotoxic. Again, so it's chemistry questions that will drive a lot of these things. But like PDMS too, PDMS was also cytotoxic for neurons, and then people found ways to solve it. So I think there might be solutions there as well. Thanks. Okay, then let me shift gear here quickly for the second talk, part of this talk, so we spoke about assays, ELISA. This is kind of the concentration range where we're at. But theoretically, if you have one molecule in your blood, I think that's 10 to the minus 25 mole. Maybe practically you could certainly clinically have something relevant at 10 to the minus 21 moles or so. And we have ultrasensitive assays that can go up to 10 to the minus 18 moles. And so they give us access to molecules. And we think about early diagnosis, cancer, you want to detect it when it's very small, the concentration in blood will be very, very small. Right now, we cannot detect that. Or we can detect that a little bit, or we can detect it actually better with ultrasensitive digital assays. So the big pioneer and also commercial success, because a lot of people try and a lot of people publish, but in practice, getting the reliability and the specificity is actually the big challenge, because they work once in the lab for a paper, but they don't really work reliably. And so Simoa, that's the technology that can do that. And so they shift from an assay that's continuous, analog, to an assay that's digital, where you compartmentalize beads in small wells, and if there's one molecule on the bead, there's such a small volume inside of that well that will convert into a digital visible signal. And then you can count. So it's like digital PCR, for the ones who are familiar, but it's digital ELISA, basically. Now, the challenge is that the instrumentation for that is very bulky, it's expensive, and it's also slow, 3 to 24 hours. And so what I want to talk in the last few minutes here is about our efforts to address these challenges with what we call the microfluidic sieve and detector. This is the technology here. and it has a microfluidic membrane with a lot of holes. And the process flow is now to apply sample analyte like you would through a sieve. And then inside of these holes, you capture your analytes. And after that, like in the SIMO example, you digitally detect single analytes that are captured in there. And while SIMO takes several hours, what we're proposing is that we can do this one in 1 minute for the capture of the analytes, 4 minutes for the signal amplification, in a rapid test of 5 minutes, and achieve a concentration here for in a model case with streptavidin of zeptomolar sensitivity, which is above many of the above and on par with the highest sensitivity detection, well above what's the classical assays that are being used in the lab or clinically. And so how is this possible, and how can we make this work? And so here I want to maybe bring back something more familiar to you, which is rice when you have to drain it. It's and sieving, we all know about sieving. We have thousands of pores, and the foundation of sieving, if we think about a pore here, the foundation of sieving, the way we think about it is that the pore is smaller than the filtrate we want to filter. So we just flow it through and everything gets captured. Except when there's very small molecules, of course, they can start to clog up your pore. And that's actually one of the challenges with filtration. Well, when we speak about microfluidic sieve, it's actually a different concept. Our pores are 1,000 times larger than the analytes. So visually, that's just 100 times smaller here. So our analyte will just flow through. So how can we filter things with pores that are much smaller, pores that are much larger than the analyte? So here the trick is that pores are not just, we're not looking at the 2D part of the pore, but we look at the 3D structure of the pore, and we think of the pore as a cylinder. And we're at the microscale here, so we're thinking about, and this is actually the size of the pores we're looking at in our demonstration, 8 micrometer diameter, 20 micrometer in length. So if you have a flow of sample here, and the analytes, maybe proteins 3 or 4 or 5 nanometer in diameter, well, what will happen once it flows through? It actually undergoes Brownian motion. And the Brownian motion will lead to Brownian motion-induced wall collision, and if you have an antibody on the surface, that can bind that molecule. So just to quickly give you set the dimensions here, many of you probably know about the diffusion equation. The characteristic diffusion length is square root of d times time. D for proteins about 80 micrometer square per second, give or take. Our distance is 8 micrometers, so 4 micrometer from the center, so it's a 4 square. If 16, so it's L squared divided by D, so 4 square, 16 by 80, so it's about 2/10 of a second before we hit the wall. That's just kind of on a statistical average. And so very quickly we can have the wall, but now because our pores are comparatively very large, we have very low flow resistance, and also much limited risk of clogging of our system here. And so to illustrate that, we actually did we introduced what we call stochastic Brownian agent method, where we stimulate this random Brownian motion. And we did thousands and thousands of simulations, and we can then, through Monte Carlo methods, extract the ensemble averages. But here I'm showing you just 10 of them, where we have 10 analytes, and so we show if they flow through, this is how they would flow. Here, that's the 20 micrometer pore, that's the average position for the flow speed, and that's the random Brownian motion of our simulation here in that thing. And so in this scenario, and that's kind of the scenario, the 1 minute scenario I showed you, we'd have 5 out of 10 analytes captured with this flow speed. Now this is very tunable. If we have a lower flow speed, or the same flow speed than before, or a higher flow speed, well, this is what happens. If the flow speed is too high, well, basically everything just flows through. That's the same than previously. Or if the flow speed is lower, well, then the analytes have a longer time to bind on the surface. And here we're going to now 0.02 of a second. So I'm not sure I want to wait for the full length, but yeah, maybe we can just. So now by tuning the flow speed or the diameter or the length, I can basically play on how to capture the system. So this is all straightforward. And then how can we make this work for a rapid test? Is that we just have one pore, but we have 500,000 pore. And so we simply load the sample here. That's the setup we used. We have a parallel flow, and so we flow the sample, and then in 1 minute we have the capture. Well, that's all great, but now how do we detect it? Well, same than before, sandwich assay, flow the detection antibody, another minute, we wash, 15 seconds, flow the enzyme, 1 minute, wash, 15 seconds, substrate, 30 seconds, cap it with oil. So we partition all of these wells, and now single molecule captured in there will give a visible signal in about 30 seconds, and so we can have a 5-minute total assay time. And then we can detect it with a 10x objective under a simple microscope. And so this is image before, and then this is the image after amplification. And I think you can see at the back too here. We have, then we can digitally recognize and count the number of events. And so how can we make these little membranes 20 micrometers thick? So that's actually not something we developed previously. So here's a case with 100 million of these holes. And that's a fabrication process that was published in this paper, where we use it actually initially for size exclusion-based capture of circulating tumor cell. And now we're manufacturing at this membrane about 10 millimeter in size. And now we can use them basically to flow the samples. And like the simulation here, here's an example where we flow at different flow speeds. And then you have the analytical solution, the FEM, and our Monte Carlo simulations of these 5,000 simulations, which all very well align. And then the experimental results for this system here. And so if we have 1 minute, that's the 50% capture rate. If we have 3 minutes, we go to about 70% capture rate. Or if we do 2 seconds, then we have maybe 2% capture rate, which if you have a billion molecule, maybe that's enough for what you want to do. And what's also very nice here, if you have a certain sample and we want to flow, well, we have less volume, then we have also less sensitivity. But conversely, if you have a larger volume, we can just keep flowing through the system, and the number of analytes we'll capture is basically proportional to the number, to the volume that we flow through this system here. Now, and this is also something we didn't invent, that we've copied from Simoa. We can count individual analytes, but once we have too many, then Poisson statistics becomes not very accurate. But what we can do is we can combine digital readout, or when we have more than 50% occupancy, we have an analog readout, just take the average signal. And when we do that, we can combine it and have a binding curve that has a higher dynamic range. And so here is then the example for the streptavidin, where it's this 1 minute flow. And with that, we have a limit of detection of about, calculated from the curve, of 6 molecules in 200 microliter captured in 1 minute. And so that's exactly then the power of this array of samples here. Now let's compare this to conventional ELISA. So this is a conventional ELISA that we did, actually very good limit of detection in our hands here. And then with ELISA, we have just from the mass, you can see it's about 2 orders of magnitude dynamic range here. Oh, sorry. So this is the ELISA. This is then now the MSD test. We have about 150 times improved limit of detection, but we're 50 times faster, but 350 times more sensitive. And we have a dynamic range here. The ELISA is 1 order of magnitude, and this is about 7 orders of magnitude. And compared to Simoa and this other digital, the top of the range digital assay, we match the same performance. And so we can then now test this for diagnostics. And here's an example for influenza A, which maybe is kind of timely at this point. So we can use rapid tests, which here are widely available. And so the rapid tests are okay when you're at a high viral load, but for lower concentration, they don't give you any results. In our case, we can go down to about a few femtomoles, and again, then have the high dynamic range up to high concentration of these assays. And so we have a limited clinical study here where we tried this with comparing PCR positive patient samples and negatives, and then compare with rapid tests. And we know rapid tests exactly, they lack sensitivity, so we only detected 6 out of 15 positives, while with the MSD, we could detect all the positives, and we also had, in this case, 1 false positive, this compared to PCR. But I would argue maybe we are actually a real positive, because for each virus, there is 1,000 proteins. So we have a 1,000-fold signal at the starting point compared to PCR, and that's one opportunity. So here I showed you this with proteins, but with reason, can we also use this for nucleic acid detection? And so here we looked at microRNA, and that's our test again, as you saw before. But here on the top, you have the RT-qPCR equivalent threshold, the critical threshold, so where your PCR would detect. And so PCR in our hands had about a 2 femtomolar detection. And so we're just close to the PCR or rivaling with the PCR performance here for this microRNA detection. But now one of the big advantages I told you is that we can have flow through. So if I just flow through more sample, I can just improve my limit of detection by basically increasing here the flow to, I think, 5 milliliter. So it takes me now 25 minutes for doing the full assay. That's still faster than the 1 hour I got for PCR, and now I have a limit of detection that's actually beyond or outperforms the one for PCR. Exactly, okay, here, up. Okay, and that's basically then the wrap for this part of the presentation. So I showed you the microfluidic Sieve-Detector, so it's, I think, conceptually quite straightforward and also fairly, hopefully, simple. And so a microfluidic sieve, large pores, in situ capture and detection. 1 minute capture in 200 microliter with 500,000 pore for a 5-minute test. So that's kind of what you see there on the top left. And with a concept of what we call the Brownian affinity trap, because you go in and then it's Brownian motion-induced affinity binding on the wall. And that's supported then with this stochastic Brownian agent modeling, which I think is fairly, maybe you could tell me, but I'd never seen anyone doing this kind of Brownian motion simulation. And so it's kind of not that complicated, but it's very informative intuitively. So I hope maybe other people will start to explore that. And with that, we get an attomolar sensitivity, zeptomolar for streptavidin, still with room for improvement, I think. We have low CVs, as you can see on the binding curve, so we can get precision along with an extended dynamic range. And we can even outperform PCR on its own turf, I would argue. And so with that, we see really excited about the potential for this for an affordable, easy-to-use point-of-care diagnostics. And we're also looking then at commercialization opportunities for this system. Okay, and then with that, thank you all for your attention and happy to answer additional questions you might have on either part of the talk. Thank you.
Any questions any audience may have? Yes, please. Questions here.
It's very exciting to see these microfluidic sieves. But maybe I'm wrong, but correct me if I'm wrong. So seems like you're relying on the antibody for specific recognition. What about I want using this technology, look at, let's say, bacteria. I mean, I don't know which kind of bacteria I have in the water, let's say, E. coli, Pseudomonas, I mean, either one. But if I'm using technology, it seems like I'm limited to look at only one type of bacteria, which I know, but there's like billions of bacteria out there, right? So.
Okay, so I mean, so for bacteria, I'm sorry. You'll have to go back to size exclusion-based filtration. So the premise here is Brownian motion, right?
Yeah,
bacteria
sorry,
will have a very low
diffusion. Yeah, I know, but take an example. What I'm saying is you need a specific antibody looking at the molecules. But let's say I don't.
Yes.
The thing I want to look at doesn't have, antigen on the surface.
Yes. So okay. So and that's actually a great question because there's lots of assays, and lots of fancy technologies and label-free and all that. But when you have an assay, you often get a signal. And the question you always have to ask is that a real signal or is that noise, right? And so we really and the antibodies are actually quite extraordinary in terms of the sensitivity and specificity they can give you. So you need you could also use, of course, if your target is nucleic acid, you can also use base pair recognition, but you need something that gives you specificity. And so the antibody is a very powerful tool, and also has with the fairly high on rate, it also gives you the opportunity to capture the good rate. And I didn't point it out, but not every collision leads to binding, right? And so we did calibrate that. So in the model, so it's the binding probability upon collision in our model is 1.5%. So most collisions actually don't lead to binding. And we spent actually a lot of time optimizing the surface density and so forth. So yeah, so you need something that will have a specific binding in that system. Now, the strength of the system is speed and the rapid detection. It's not multiplexing, at least not here. Now, if you want to multiplex, I mean, I think that was one of your questions too from under. Yeah, you could have different zones that you could, of course, functionalize with different targets, or you could have multiple filters stacked on top of one another so that you could then detect them differently. So there's ways that you could do limited levels of multiplexing at least. Maybe not 1,000-plex, but 10-plex. I think 10-plex certainly something that you could think about.
Is it possible like put different type of antibody in the same channel?
Yeah, but then you don't, I mean, okay, if it's an enzymatic signal, you don't know which one you bound, right? And then also your capture probability would go down because now your density of particular antibody would go down. So maybe it's easier to have, let's say, 3 different zones with each a different antibody, so that when you get a signal, you could at least, I mean, it depends what you want. If you don't really care, you just want to say yes, no, and then you could just have all the antibodies in the same well. If you want to know what it is, then you need to have some spatial separation. Or then if you have different enzyme products that have different colors, then you could have them in the same well and just look at, like say, or if it's fluorescence, if you have single molecule fluorescence readout, then you could also have that in the same well and then have a colorimetric or barcoding way of reading out what is in there.
Okay, all right, thank you.
Yes, please, Cecil.
The scanning. So at the end, can you estimate how long it takes to finish all the scan in order to get to the entire chip being scanned?
Yeah, so that's a great point. I mean, we don't. So it's a 10x objective. We did maybe 10 or I don't remember how many images to cover the whole entire area. Now now the whole thing is manual, right? It's the student, like the show, he puts the pipe, it has a syringe pump, and then he puts it on the microscope, and the image is on the microscope. Now, when you have like a high capture rate, like here, I don't need to image all the surface area. I just take 1 or 2 fields of view, and I already have enough statistics, right? Yeah. If I have very few binding events, then I'll start to make sure that I start to take more and more image, and you could, of course, dynamically adjust that, as you make the imaging. But and then yes, if you have fast, large field of view imaging, then that could help you speed up the readout of this.
So the total time from the sample to answer is approximately how long?
5 minutes is the time you get signal roughly from the fluorescence. Now, I mean, the imaging is manual, so if it's just one image, and then okay, we don't have then you have now it's a digital processing is not really fully integrated, but I mean, all these things can be, if you have a reader or even just a microscope, you put it in and press start, it could do it very quickly, right? Because the sensitivity is not very high that you need. So a 10x objective is good enough to get you this type of, so that's what we use right now to get these images. Maybe if you have a better camera, you can use a 5x objective, then you could have a larger field of view, or you can come up with other ways of detecting them as well. Yeah, but I mean, it's not, right now it's not fast, but it's not optimized either. And I think it's not I don't see major technological challenges of making it in a simple reader that you could do it fairly quickly. Yeah, I think there's a question there. Yeah. Yeah, that's a great question. So like I said, this was used for circulating tumor cell capture. So the thickness, and it was a size exclusion. So we want to have low flow resistance and mechanical stability of the membrane. So there's the mechanical stability. And these are replica molded membranes. So then the aspect ratio, where you can still separate it from the mold, becomes also a challenge, right? So if you want to do higher aspect ratio, it becomes really ever more difficult to separate them. So if you have a different the great thing, it's a molding manufacturing process. So we can make at once fairly large areas on this at fairly low cost. But it will have limitations on the maximal aspect ratio you can do. If you do silicon microfabrication, yeah, maybe you can do higher aspect ratio, or you have another manufacturing process, you can do higher aspect ratio. But the great thing with the MD700 is, so it's a fluoropolymer, it's quite robust as well. So if you do silicon, so we tried other membranes in the past in silicon or in in SU8, but then silicon is very brittle, and SU8 is also brittle and kind of it's not flat when you mold it. So the manufacturing is a big aspect. The manufacturing and manipulation is a big aspect on why, and this works pretty well for this approach.
I think this is also like the microwells for cell capture, and maybe you can use each pore to capture a single cell and to use the antibody on the wall to test their secretions, because that can also give a very high sensitivity than the current ways.
Yeah, that's a great idea. No, I mean, we use it for circulating tumor cell capture. So we just have, but we didn't use the well to measure secretions. So that could be a great way of expanding it. Now this, I mean, the dots are large, but if you have a cell, right, the Brownian motion is going to be very limited for things that are micrometer scale particles. So this Brownian affinity binding works really well for maybe nanoparticles, say up maybe 100 nanometer up to 200 nanometer. After that, I mean, you can count the Brownian motion, or then you have to make smaller channels. But for cells which are tens of micrometer, Brownian motion is going to be very limited. So I don't think that I mean, yeah, it's a good. I mean, I don't know where it's the upper limit, but the smaller the better.
Yeah, I see. Thank you.
Thank you.
Any other questions? So maybe may I ask? Essentially, this is not dissimilar to a very fancy way of creating a very high precision filter paper for like a rapid antigen test. So what is the stage of translation and commercialization of this? And if I think for the users, the experience could be similar to what you would typically do for a rapid antigen test, but because of the very carefully engineered membrane, the sensitivities and other parameters could be very different.
Yeah. I mean, we haven't even published it yet, so. But I mean, it's a preprint, right? So yeah, so you can have rapid tests or lateral flow assays for influenza and whatever, or COVID. But what we know is that, and not about here, but in Canada, there was a big debate whether these were sensitive enough and not, and this and that. So the current tests is for many conditions, they're not sensitive enough to really, or also like the experiments I know, only 6 out of 15 who are PCR positive were positive on this test. So the current tests, people use them because they're fast, convenient, and have a good enough sensitivity at the high viral load. So here the opportunity is to have a test that is simple to use, and thanks to the digital readout in particular, then you could have a sensitivity that matches PCR and then really give you a much more accurate readout. So it could be both used then for existing, like similar for like this respiratory disease type of application, but now you really have high sensitivity, so much more high confidence. Because you could have these tests, they can be negative and you still cough and you still don't know what it is. Here, you're much more likely to detect it. Or you can start to then also look into ultra-sensitive biomarkers, for example, neurological biomarkers, there's quite a few of them now coming up as well. And open up new biomarker opportunities where because we know early disease detection, we want to measure things at low concentration, but we had no tools to measure them. So now we have the tools where we can measure things, and so we can push back basically the point at which we can diagnose things. Now, the challenge there is we have to identify the biomarkers first so that we can implement them on these type of assays. But here what might help us is that there's a few companies now that do like up to 200 plex ultra-sensitive assays. And so once you have a marker or a few markers that you identify through these technologies, then you could use it here. And also what's very powerful here is that you can have ultra-sensitive and low sensitivity on the same chip, right, with this very high dynamic range. So we have the potential of, for example, in multiplexing, we could detect different markers at different concentrations and still get accurate readouts for each one of them.
Thank you. So I think if there are more questions, I'm sure Professor Juncker would be happy to talk with you after the talk a little bit more. But without further ado, please join me to thank Professor David Juncker for sharing a talk that is very relevant to a lot of our research interests and inspiring for a lot of us, triggering a lot of questions. Thank you.
Thank you.
And please continue to discuss with Professor Juncker for any potential ideas for collaborations, joint initiatives, and also maybe pick Professor Juncker's brain on some of his ideas and suggestions on some of your work as well. Thank you.